Hello class, welcome to the next segment in lecture 23, and in this segment we're going to take a look at some of the features in the atmosphere that can favor significant straight line wind events. So unlike the previous segment where we took a look at favorable versus unfavorable characteristics, straight line wind events, there's actually a number of different physical processes that can come into play to produce straight line winds. So if you're going to really make favorable versus unfavorable characteristics, like a column for each of those, it would just get really complicated. So here we're just focused mainly on the things that can be present in the atmosphere that can produce straight line winds. And there's two main mechanisms that can produce strong straight line winds. One is a microburst, which is basically a very forceful downward moving current of air, which as it hits the ground, it spreads outward. And if the current of air is sufficiently strong, then that can produce damaging straight line wind gusts. But the other mechanism that you can have is more of a derecho event or a squall line. That is, you have a line of thunderstorms that is producing wind damage, and in the case of a derecho, is a long-lived line of thunderstorms that's producing widespread significant wind damage. So with that in mind, let's go ahead and take a look at the favorable characteristics for straight line wind events. There's this parameter called Downdraft Cape, which is often abbreviated as D Cape. So regular Cape is an estimate as to how much energy an updraft will have. Downdraft Cape is an estimate as to how much energy the downdraft in the thunderstorm will have. And ideally, you look for values over 800 joules per kilogram to determine if those downdrafts are going to have enough energy to produce damaging straight line wind gusts. And ideally, higher values of D Cape indicate greater potential for damaging straight line winds and greater potential for more significant downdrafts. And if you're looking to get a microburst event, ideally what you want to see is a deep and very well mixed boundary layer. And this will typically show up in a sounding as an inverted V shape. That is, if you take a look at the dew point line, which is shown in green, and the temperature line, which is shown in red, those two will form basically an inverted V shape. And we'll take a look at an example of what we mean by inverted V shape. And also, if you're looking to get a derecho event, ideally you want to have a large difference between the air parcel temperature and the environmental temperature at, say, a height around 500 millibars. And there's actually a parameter that reports that differential, and it's called the lifted index. Ideally, you want, say, a value of -10 or -15. Negative values indicating a air parcel that's warmer than its environment. Positive values indicate an air parcel that's cooler than its environment, a stable atmosphere. But ideally, you want a very negative value for a lifted index. Usually, you want a value of around -10. You can get values even lower than that, like -15, in some extreme cases, close to -20. Which, if you get -20, you've got a very explosive atmosphere in place. But usually around -10 is when you might start raising a red flag that, yeah, there might be enough energy here to support a derecho if all the other conditions are favorable. And ideally, you want to have strong mid-level winds, which will give you fast-moving storms, which, if you have storms that are moving faster, they have the potential to cause more widespread wind damage. Now, something that's kind of interesting is you can actually get a fairly significant straight-line wind events without a whole lot of thermodynamic support, but if you've got extremely strong mid-level winds, those storms are really racing. Those fast-moving storms, even without the thermodynamic support that's highlighted up here, that is the high D Cape, the well-mixed boundary layer, or the large parcel temperature differential, the large differential between large differential between air parcel temperature and environmental temperature. Even without all this, just this factor alone, the really strong mid-level winds causing fast-moving storms, that alone can be sufficient to cause straight-line wind damage and potentially widespread straight-line wind damage. But if you've got a combination of very strong mid-level winds and all this up here, now you're talking about a greater chance at a much higher end wind event, say something like a derecho event. And ideally, you want linear storm modes. And again, it's possible to get damaging wind gusts from supercells, especially with the rear flank downdraft, which is a downward moving current of air that occurs on the backside of the supercell. But ideally, to get a lot of widespread wind damage, you want linear storm modes. You want a nice line of thunderstorms for damaging straight line winds. And something that can help generate significant straight line wind damage is if you've got strong turning of the winds in the lowest 3 kilometers. So we kind of highlighted this in the criteria for tornadoes. If you have strong turning in the lowest 1 kilometer, then you're going to have stronger rotation potentially within the thunderstorm. You can also, ideally, you would see if you wanted, say, mesovortices, which are tornadoes that form within squall lines, embedded tornadoes, which are a real pain to issue warnings for. Just ask any National Weather Service forecaster about that. But if you got strong veering in the lowest 1 kilometer, then you've got an atmosphere that's potentially favorable for a lot of spin-up tornadoes embedded within the line itself. But if you've got strong veering in the lowest 3 kilometers, then you've got a better chance at producing what are referred to as bowing segments or bow echoes, which are basically pockets of locally intense locally intense straight line winds. And you've probably seen this on radar before, but it's basically the highest reflectivity will basically assume a shape of sort of a comma or a parenthesis, and within that feature you'll see very strong winds usually. And also for straight line winds, ideally you want to have high LCLs. So we kind of alluded to this on the previous segment about tornadoes, where if you have lower LCLs, you have less evaporative cooling, so your downdrafts aren't as cold. But if you've got high LCLs, then you're going to have more evaporative cooling, which means you're going to have much more rapid downward acceleration of the descending cool air. And that's ideally what you want to see to get a significant straight line wind event. And if you're looking for a derecho setup, most derecho setups have a southwesterly wind at 850 millibars and a westerly wind at 500 millibars. But again, sometimes the southwesterly 850 millibar wind can be a bad thing. It can limit the amount of storms that actually go up. And ideally, this is what you would look for in, say, like the upper Midwest, which typically is the region where you find most of the derecho events during the summer. This setup doesn't work particularly well in the plains. I was kind of curious about the plains. For a derecho setup in the plains, ideally what you want to see is a strong northwesterly component in the winds once you get into the upper troposphere, which is kind of odd to think about, but most of the big straight line wind events that occur in the plains have a setup that's something like that. But in a place like the southeast or in the Great Lakes or the upper Midwest region, ideally you want to have a southwesterly 850 millibar wind and a due west wind at 500 millibars. And that due west wind at 500 millibars, we'll talk more about this in the Synoptic Scale setup, but this due west 500 millibar wind is really what you want to see to really get those storms moving. So if you have those fast moving storm motions, then you got a much more heightened potential for damaging straight line winds. So let's actually take a look at some soundings. So if you're looking to get a microburst event, this is ideally a thermodynamic profile that you want to see. And this is what I was talking about when I was referring to the inverted V shape. If you look at the trace between the environmental temperature here, which is the red line, and the green line representing dew point, if you look at that, you can see how it forms this sort of V shape. And of course, a V is not shaped like this. This is actually a V that's been flipped upside down. But this is ideally what you want to look for. And in the most ideal case, you'll see the dew point line hugging a line of constant mixing ratio. So these green lines, these faint green lines that you see here are, I believe they're called isohumes, which are lines of constant mixing ratio. Ideally, you want the green dew point line following one of those lines almost perfectly, almost running parallel to one of those lines. And then ideally, you want a red line that's following a dry adiabat. And if this extends to a really deep height, so in this case, you've got a very well mixed boundary layer that's extending up to, I'd say, around 2 kilometers, maybe just above that. If the deeper this feature, the better the chance that you're going to have much more intense microbursts. And this is the feature that you would want to look for diagnosing the potential for microbursts. You want to see that sort of inverted V shape between the dew point line and the temperature line. So if you get a thunderstorm forming in such an environment, then the downdraft is going to have a lot more power behind it, which will give you a better chance at producing some straight line wind damage. And something else that might be worth noting, so in this case, the Downdraft Cape in this sounding is almost 1,500 joules per kilogram. So definitely, if we can get a storm going in this environment, it will have a shot at producing some fairly intense straight line wind damage. And this is something that you might see more of in a derecho setup, where you're going to have a very high cape and more of a southwesterly wind, again at 850 millibars, going to westerly at around 500 millibars. But you also need to look at the Synoptic Scale setup. There's some Synoptic Scale features that you have to look for to really determine if you're going to have some sort of derecho event, which again is a long-lived and very intense windstorm. But if you just look at the parameter space here, so again, you don't really have the strong veering present. The wind field's kind of weak in this case, but we do have a southwesterly wind going to westerly as we go from 850 to 500 millibars. But just the parameter space here, the Cape values are just absolutely ridiculous. This is there's if to say that there's energy in this atmosphere would be a just a gargantuan understatement here. And if you look at the Downdraft Cape, it's around 1350 joules per kilogram, which is again above that 800 joule per kilogram threshold that we outlined earlier. The LCL heights are not especially low in this case, so your downdrafts are not going to have a lot of evaporative cooling, but you're definitely going to have some very intense thunderstorms going up in this environment that will be capable of producing some very forceful downdrafts. And the Lifton index here is about -16 to -18. So if you look at 500 millibars, this dashed line represents the air parcel temperature, and this red line represents the environmental temperature. You can see there's a massive difference between these two, which means those air updrafts are going up when the storms go up in this environment. But that's going to do it for another feature that you can look for before I wrap this up. Just like with tornado events, ideally you want to see a very steep lapse rate near the ground level, which will help accelerate those air parcels downward, help accelerate those downdrafts downward. But that's going to do it for this segment on dimensioning straight line winds. And in the next segment, we will be doing the same thing, outlining some criteria for large hail. So with that, I will see you all in the next segment.